And so I'm very happy that we could get Kelsey to come and speak. So Kelsey Hightower is 4 months now at this. It's a new company, so nobody's there too long, but you've been there for 4 months now, and he's their lead open source evangelist, and it's going to talk about, at least that's what it said somewhere about you.
We're a startup, so we have like 8 titles.
There you go, okay, yeah. So I'll just turn it over to Kelsey, and he can correct me and tell me all the real scoop. And let's everyone welcome Kelsey Hightower.
All right, we're going to take this whole screen. So I'm not in control of it all, just some of it. All right, so we're going to talk about CoreOS. I'm going to try to do less of a product pitch and more about the technology. So there'll be, majority of this will be demos. The only slides I have are to paint the overall picture of what we're doing, right? Because a lot of this will be on the command line. But what I'm going to try to do is set up the concepts of all the components that comprise this idea that we call CoreOS. So CoreOS is a collection of technologies and opinions about how we can actually get to this place called modern utility computing. So today we have a bunch of operating systems that are, you know, from, I guess, the 80s, the legacy is carried on, except for we got package managers to automate software installation. And we got a bunch of tools to orchestrate that. So CoreOS takes another look at that and say, how can we make even the operating system itself disposable? So a little bit about me. My name is Kelsey Hightower. I put my Twitter handle up there because marketing loves when people tweet. So if you feel the urge to tweet, please tweet. The title I'm using today is a developer advocate. And what that means is I actually write a lot of code for our particular products. I contribute to a project called Kubernetes, which is a container orchestration platform by the Google team. I have a couple other projects, and I consider myself a toolsmith and a gopher because everything we do at CoreOS is written in Go, except for the kernel work that we have to do for the operating system. So CoreOS, at the very foundation of CoreOS is Linux. So we use the latest stable version of Linux. So we don't do what you would see in an enterprise distribution where you take, let's say, Linux 3.14 and you maintain that for 5 years and a bunch of patches. We don't do that. What we do is we follow stable. So if there's any bug fixes that we fix or we need fixed upstream, we push it upstream, a new stable release gets cut, and we push that out to all of our customers. The next portion that we're built on top of is systemd. So systemd, if you don't have experience with it, it's people rethinking the whole init process and starting up a machine, and what does it take to build a user space collection of tools that represents the rest of the OS. So you have this kernel, and with that kernel, you got to have that machine be able to boot, start, and manage services. And systemd attempts to kind of unify all of those user land separate bits into one unified system. You know, it has some drawbacks, but we'll talk about some of the benefits here. And one thing unique about CoreOS is we recommend, and actually the only way to do things is to either A, have a static binary, but what we like people to do is run everything in a container. And right now that container format is the Docker container format. And we'll talk about the differences between a container format, the thing that you ship around to servers, and the actual runtime of launching that container into a process using the kernel features to give you containment. Right? A lot of people trip up over those two concepts, and they are different. And then we talk about the update engine. So this is one thing that the founders of CoreOS really took to heart. You know, one of the biggest things for anyone that has done any system administration, once you have a bunch of servers up and running, you're very reluctant to update those things because there are all these little pieces of updates that come in over the period of lifetime of a server that could cause problems in your infrastructure. So what we do in CoreOS, we separate the user, your applications, from the OS. So the OS in CoreOS is read-only. You can't put any extra bits once the OS is booted into user. It's read-only. You can't do anything. So that gives us the ability to upgrade without impacting your applications. The only contract we have between your app and our OS is the kernel. And you have to run everything in a container, so the only thing we have to keep compatible is the kernel, which in the Linux world is pretty stable release after release. And then Docker. Docker is our container runtime. So the Docker is a very popular format in Linux container space. And XCD is also a central service that we use, and we'll see this in a demo. And when we talk about distributed computing and running at scale, one of the formulas that most people are missing is a service like XCD. XCD is that centralized component that allows you to synchronize your cluster state. So in order for these machines to talk to each other, lock management, things like master election, you need a central service like this. What a lot of people end up doing is reinventing those primitives in their applications, and it gets really complex because every time they do a new application, either they have to import the existing library and try to make it work, but the problem is it only works for your apps. When you bring in another app, it can't consume the lock service for the whole cluster. So having a generic bit there enables lots of things, and we'll see a couple of tools that we've written, mainly a distributed router that gives us an overlay network to build a mesh between a cluster by keeping the router state in etcd. And then Flannel. Flannel is, so with containers, one thing that's nice about them is you have all of these little services in a container that you can just launch. But the problem is they don't talk across hosts by default. So to fix that issue, what we've done is we developed a tool called Flannel, which will basically build an overlay network across all of your clusters of machines. And this facilitates a model where every container gets an IP on the subnet. So that means every container becomes a first-class citizen. So by default, Docker out of the box, you get a Docker bridge, and you end up with a collection of IPs that are not accessible from the outside world. And then you end up having to deal with random ports being mapped back to your application. While this works, it does add a bit of complexity. And then your containers can't talk to each other. Flannel solves that problem. And then finally, we're going to show off Fleet. Fleet is a scheduler. So the idea with Fleet, if you're familiar with any internet system where you get on the box and you say, service start my application, well, Fleet does that from a cluster view. Fleet takes a step back and says, I can actually schedule services anywhere in the cluster. So if you have 100,000 machines, you can give Fleet your unit files or your service specification, and it will launch it to the best host in your cluster. So you don't necessarily log on a machine and start stopping and running services. You do this from a cluster view. So what we're going to do today is we're going to build this up from scratch. We're going to launch a machine. We're going to show how we use Cloud Init to configure that machine. And then we're going to play around a little bit with the tooling to see how all this works. This is very interactive. So if you want to see something, like, hey, what happens if you do X? Raise your hand, ask me to do it. I'll attempt to do it. No guarantees it's going to work, but I won't be shy and we'll do it. I'm going to go through a few slides so you guys can get your mental picture. So first, the update model. The update model really comes from the idea when Chrome came out, one of the best features about Google's Chrome web browser was it did automatic updates. And the reason why that was important, there was a dark period of time where web standards really reached a great point, but no one had access to the features because no browser would update to change those engines. So what Google did was it took the choice away from you. Just say, you know what, we're just going to push an update to your browser, and the next time you open it, you're going to be running the newest version of Chrome. And most people didn't think about it because it was an automatic, not just in download, but it was an automatic application. So now you ended up running the newest version of Chrome every time you restarted your browser, and sometimes it would just annoy you saying, hey, there's a new update available. But once we did that, they started a trend where every browser now does this, and now we can get web standards to everyone much, much faster, right? Because they're easy to get. So we took the same concept and said, what if we did that at the operating system, right? So what we do is we have two separate partitions. And anyone with networking experience, you do the same thing in networking gear. A lot of times there's hardware that you ship to a customer, and you really can't mess up the pristine install because you don't get another chance. You know, you have to do a recall. So the best thing you can do is update a separate partition with the updates. And then if it's good, you switch over to that partition, you boot up. If there's any problems, you can just roll back atomically to the previous version. This is a very important concept because it allows us to do atomic updates and then just reboot a cluster, and if things go awry, you flip back, all right? So we do this by default. You can turn this off and maybe just do automatic downloads, but not updates. And most people that have experience with Docker, just a quick show of hands, how many people have played with Docker at all? Okay, so about half the room. Should I explain what Docker is at all? I will. So, idea today, I've been a sysadmin probably longer than I've been a developer. And a lot of times in the sysadmin world, you'll write this application, let's say you're writing some Java. And you write all this code, and it has a bunch of dependencies, but you feel that someone will sort this out for you, right? There's a build system that has Maven, and it will resolve my dependencies. And there's a sysadmin somewhere that will deploy my app to the right OS, to the right JVM version, and they're just going to do all the right things for me, and nothing will ever be broken, and it will just go to production. That, for 15 years, never happened, right? I think half of the movements in IT now around that very problem of this big miscommunication about how to build and deploy an application. I think half of IT is about deploying applications. So that model that we have today before containers was you log into a server and you try to follow this build guide. And now we have tools like Puppet, Ansible, and Chef that try to create recipes for how to build these things. And the analogy I like to use is like the post office. Back in the day, if you had something you wanted to mail to someone, they'll look at it, put a stamp on it, and send it on its way, right? But the thing is, that's very inefficient. You need a lot of people to do it. It's very clumsy. And then some smart guys came around, FedEx and UPS, and said, we don't care about what the thing is. It just needs to fit in one of these boxes. And as long as it's in this box, we're going to put a label on it. When we put a label on it, we can put it in our trucks. And then we can actually pack our trucks much more tightly because we're going to force you to put it in a box. You don't need to tell me what you're shipping and why. Just put it in a box. This is what Docker does for your application. And we're going to actually use Docker to deploy an app, and we'll see it here today. So instead of you telling your sysadmin, you're a developer, and you want to use a new library, instead of having a meeting and doing a negotiation with the sysadmin team, you just build a new Docker container, and you push it to a registry, and you ask them to deploy what's in the box. And the only contract you have at that point is, there's a service in that box that binds to this particular port. I just need you to run it. And whenever you feel like you want to update that particular box, just put your new bits in. You want to change the JVM, you want to change the underlying OS because maybe you need a different set of libraries because you're dynamically linking, you can just do that. So now the contract has changed. This is what made Docker so powerful and people are so excited about it because now you as a developer, you can check in your Docker description file right into your source code and just do Docker build and package up your app and just turn that over to someone. So what everyone's excited about is that having the standard format makes the OS less important. You don't need to worry about Red Hat versus Debian versus Ubuntu. You can pass around this one box. And today, Docker announced that they'll be doing the same thing for Windows, right? You can't just reuse a Linux container on Windows, but you have the same primitive. You as a developer, you put it in the box. So we're starting to see this trend to move away from individual packages and specifications to self-contained things. And most people will be suspicious, like, why would this actually work? Well, the mobile platform, when it came out, you didn't deal with installation problems. There were no wizards and next. You went to an app store and you downloaded it, and it was self-contained. This is why the iPhone works so well. Everything is self-contained. There isn't like, well, you're about to download this map app, but we need you to go download this other thing first. There was none of that. And that's what Docker does for your application. So so what you need is a Docker host. So on CoreOS, by default, we were the first operating system just to bake Docker in full stop as part of our build. So when you launch a CoreOS host, Docker's just running out of the box. So what you can do with a single node is something like this. You can deploy a collection of applications on the machine. Then once you have a collection of machines, you can start deploying different apps on different Docker hosts. And right there in the middle is what we use for distributed configuration, right? So if you have a web front end, you may want it to talk to a database server. But instead of hard-coding your configurations, you can actually push them into your XCD key value store and allow the services to have a conversation. If you're a database server, announce yourself to XCD that you're the database. You may put in your username and password or whatever metadata is required to use your service. And another service can just read the key from XCD and not be concerned about where you've been deployed, right? And we'll actually see some of that today. And
so
go ahead.
So how do you partition that among apps?
This is the meat of it. We're going to actually show what a scheduler does, right? So most people that have a sysadmin team, that's your scheduler, right? You say we have these 5 or 6 apps that make up the stack, and then they go and figure out the database goes on this server, the apps go on this server. And there's a bunch of inputs that they use to make that decision, like these are in a DMZ, right? So there's some metadata that they have in their mind about a specific host and why it's the best to run your application. And we're going to see how tools like Kubernetes and Fleet encapsulate that decision-making capabilities and become your scheduler. So if anyone's ever heard of like Mesos and tools like that, this is what they're attempting to do. Take that information out of your dev team and your ops team and put it into the scheduler, and then you give your scheduler the app, and it partitions things up.
I guess I was more curious about sort of a multi-tenant environment where you might have a rogue container accessing or announcing to etcd and getting access to all this other
Yeah, so security is tough. Like if you have to be locked down multi-tenant and you're in an organization where you got untrusted apps, you're going to be very, very complicated situation. You probably need to use VMs full stop if you want real security. You're probably going to have to partition everyone with their own XCD, own username and password. But there's a lot of companies that don't fall in that category. You can actually paint a small bubble for different parts of the organization where they're fully trusted. So the host that you give out should just be trusted so you don't have to introduce this complexity. I've seen some of this complexity. It's so complex that no one can use the system. So if you want to go to this scale and this convenience, you're going to have to make some compromises somewhere. So it's not lock down everything and give yourself some room to breathe.
I'm new to that, so please allow me to ask a couple of dumb questions.
Okay.
You mentioned key. So key identifies a specific container.
So we're going to actually see that in the live demo.
Okay.
So for the XCD keys, is it not possible to, set a permission on a key?
Yeah, so we're adding that now. So we're doing a lot of work with Google for their Kubernetes project. And Kubernetes is using XCD in the backend, and we're adding ACL support. So you can have one actor will have a key, and it will give it access to specific keys. And then you can have a larger authentication system to validate access to that key. But you don't want to get too complicated here. Google's been doing this for about a decade now. Their numbers are 2 billion containers being deployed a week. You don't get there by trying to have it piecemeal, that we can only deploy this container by this guy at 2 o'clock. It gets too complicated. You just need to build a system of trust. And things that are dangerous, you have to partition them outside of the cluster that's running the majority of your apps. And people have demonstrated to do this. Right? You can do this without being that granular. And this is a picture of our overlay network. I won't dive into too much detail, but the way we enable containers to talk to each other across hosts is we have to build this overlay network. And this is important because on cloud platforms, most of them do not allow you to do traditional networking. You don't have access to layer 2, so you can't just rely on a switch pushing your packets around. So what we do is we build an overlay network. There's one way we do it today, which is UDP and user space, big performance overhead. The next patch that we have going in is doing everything in the kernel through VXLAN. This is basically what VMware does inside of their tools. Is why the network overhead is very low on a good VMware setup. And we're actually going to build this overlay network when we set up our cluster. You're going to see how little steps this stuff takes. But the ideas that we want to present here is this. This is what you end up with when you go to a different model where you have a collection of hosts that can run these Docker hosts, that can run any number of containers. And that little black box, that is your scheduler. So popular schedulers are Mesos. Kubernetes is running Rising and Linux. We have a tool called Fleet built in. And this fundamentally just changing how you deal with applications at your company. Now everyone has rules and contracts against the scheduler. So you, the developer, say, I need 6 of these instances running. You give it to the scheduler. The scheduler makes sure that your instances are running. And we're going to see this in the demo. So now your ops people focus on keeping that up and running and healthy, not deploying applications. And when you go into this new model, it's much easier to roll out a new app, right? Because you know that at the end of the day, you got to put it in the box, and you're going to give it to the delivery service, and it's going to push it out, full stop. So these are what production clusters look like, right? So a lot of people want to know, what is the formula for running one of these? Well, the biggest formula, remember I told you that the XCD service is actually the most important part to a lot of this. Usually XCD can be used to bootstrap an entire data center. So if you look at some of Google's layouts, they have one big cluster that's called a different name, but it's been popularized by a paper called the Chubby paper. If you read about it, they talk about the centralized service. XCD was built from that particular paper, or the ideas contained in that paper. And once you have the centralized configuration store, you can easily provision as many machines as you want, and we're going to do that now. So in this demo, we're going to do something that looks like this. We're going to have a single XCD node. I'm going to bootstrap it a little bit of configuration, and we'll play with the keys and values to see what that looks like. And then we're just going to spin up additional machines using just a simple boot process and a bit of configuration. And then we're going to play with the scheduler so we can all get the concepts. And we're actually going to deploy a Docker container so people can see what that workflow looks like if you're a developer. All right, so now that's all the slides. And if you have questions, please interrupt, but we're just going to go straight to the command line now. And I'm just going to go step by step. So our goal now is to build something that looks like that in a collection of virtual machines on my laptop. No questions yet.
One point. Since the topic of today is the massive server, how big this cluster can become?
So this is what we're going to show.
Oh,
Right, so the idea here is that you should be able to add as many nodes as you want as you have capacity, right? So one etcd cluster can probably handle, you gotta remember, the data that you put in etcd is small. You know, this is less than 25 megs of data for your cluster configuration. This doesn't replace Redis, MySQL, it's not for that. This is strictly for cluster collaboration and configuration data. A lot of people make that mistake by trying to take a web app and put session data in etcd. It's not what you want to do. And it's the reason why they do that. It's a very attractive data store because it has a rack protocol built in, so it has good self-recovery characteristics. But there's a penalty for doing this automatic leader election and automatic failover and master election. It's very expensive on the wire, so you can't have it trying to run a big data workload just for your critical parts. Let's just build this from scratch.
How quickly does the metadata in etcd typically change for configuration?
Well, I mean, that can go fast. So if you look at something like Cloud Foundry that uses etcd behind the scenes, I might have the numbers wrong, but it's like 30,000 reads and writes per second, right? So it can be a lot of state, but the state is small. It's like, this machine should be running this container. This is the IP address of this particular database. Here's the new password. So you have a bunch of chatter on the wire.
And what about convergence?
So that's what the rack protocol does for us, right? So what we do is when we get it right, let's say we have a 3-node cluster, you guys have to use my visuals, and you ask me to set the password to foo. What I'm going to do is take your rights, and I'm going to go to my 2 other nodes that are part of my cluster that make up core. Now, I need just one other member to agree on that right before we go. So at a very high level, the way the rack protocol works is I will take that right, and I will do that at a certain index. And if I'm the master, I will take that right and say, we're at index number 1, right? This is where we are for the whole entire tree. I'm going to talk to these other guys and say, all right, guys, I have set database password to foo. I need you guys to agree on that. And they say, yes, we have that. We're ready to commit when you tell us to. All right, we're going to do that at index 1. All right, you commit, then I commit. Once we've all kind of agreed on that, then I can come back and say that is the actual value. So it tries to do this by doing that real-time replication, getting consensus, and then reporting back the value. If I were to die, that write doesn't go. So there's not a guarantee that it's going to write, but we're going to guarantee that we all agree. So if I were to die with no intervention from you, I'm the master and I go away, these guys are waiting and doing heartbeats because they're racing to be the master themselves. So what the rough rack protocol gives us is this automatic election cycle. So behind the scenes, in addition to reads and writes, you're seeing a bunch of heartbeats go back and forth. And they're all asking each other, I want to be the master. I want to be the master. Did he just go away? They will try to elect themselves to be the master. And the first guy that gets enough votes from the healthy nodes, he becomes the master. And he picks up the tree and starts writing going forward. And it just does this and it just heals itself, right? So this is the characteristic you need because Nagios and responding with the pager is not what you want for this type of data, right? So with that, we'll get into the demo.
Couple of short questions. Please tell me if they're not very appropriate for you. But the question I had is you showed a picture of a diagram of a bunch of hosts. And on each host you must have multiple containers. So how do you identify a container? Is it by a key? Is it some kind of a hash? And is it different from the host identification, which may be, for instance, an IP address?
I'll just show you.
Okay.
Will that work?
I don't know, that's what
I'll show you. And if what I'm showing you doesn't answer your question, then we'll answer your question.
Okay. And the last question, you talked about container being sort of minus OS, a VM minus the operating system. Basically.
Yeah, so to me, a container, in the actual sense, is a Unix process using some kernel features to give a container, right? So the one thing you have is you have some bits on disk. Before we talk about the packaging format, you have this binary on disk. And without any container features from the kernel, you say run this binary. It goes into memory and you can start executing. There's no containment there. You're in the same namespace as the OS. Now let's bring Docker into the picture, just talking about launching. We take the same binary and you say, you know what? I don't want you to access the root file system of the host. So I'm going to give you a mount namespace. What you think of as root is going to look different from the OS. This is traditional true root, right? So now you have your own file system. I don't want you to see the network of the host. So I'm going to build you your own network namespace. So I'm going to give you a virtual network adapter. I'm going to attach you to it, and when you do IFconfig, each 0, looks like it belongs to you, and it has that. That's another level of containment. Then I'm going to also say, you know what, you can't reboot the system. So I'm going to take away a bunch of capabilities. That's it, containment. But it's just a Unix process that's using kernel features to isolate it. And for most people, that's all they really needed. They didn't need a whole operating system running, a whole hypervisor underneath. You just needed a little bit of containment. And that's what a container is. All right, so the way we build clusters in etcd, or we boot a machine, the OS itself is about 140 megs, right? We have pretty much everything baked in that you need, the kernel, the Docker, all those things, but we do need to do a little bit of configuration. Maybe you need a static IP address. Maybe you want etcd to run in a certain way. Maybe you want to add metadata for fleet that could be used for scheduling decisions. In order to do that, we use a tool called CloudInt, which is baked into the operating system. This was made popular by Ubuntu. When that cloud era came out on AWS, Ubuntu saw a need to allow you to configure a machine before it starts. So during the init process, we run this process using a cloud config file. We rewrote it from Python to Go because everything in CoreOS must be in Go, and we like the way we can distribute things with Go instead of Python. So we're going to look at one of these files real quick. Don't get lost into the sea of text. I want to walk you through some of the sections, but don't worry about it. So this is a cloud config file. On this line, I'm setting the host name. So this host name will be etcd. This CoreOS section is basically a YAML file, and this is some metadata about what I want to happen. So there's a tool called Fleet, and Fleet stores all of its cluster state in, you guessed it, etcd. So I'm telling this first node where etcd is. It's only YAML localhost. I'm giving a little bit of metadata. This is arbitrary key value pair. Here it's just called role etcd. Here's etcd configuration. Since etcd is built into the operating system, we can configure with some of these key value pairs. Right? So basically what we're doing is saying etcd, I'm going to give you a static IP address to bind to. I personally treat my etcd cluster special. Static IPs, DNS names, service records, it needs to be there because that's the beacon of life for the entire cluster. And this is just some other cluster settings. I'm just doing an active node 1 for this demo so we can actually just get through the demo. And then here I'm just doing a bit of static networking. So what you see now, these are systemd unit files. So when you talk to systemd, systemd does have the ability to configure networking through a process called networkd. And here I'm saying match this particular interface with that name, and then give it the static IP and gateway settings, right? And then down here, I'm saying start the etcd service using systemd, start fleet, start Docker. Since Docker is built in, there's nothing to install. Here, remember, I talked about the automated reboots. I turned that off for the demo because, yeah, sometimes my machine would reboot during demo, and then people would clap as if I did it on purpose. And sometimes it throws me off. And here is my SSH key so I can actually log into the machine. There's other user management capabilities here, like you can actually even connect to GitHub and download a series of users from GitHub and their keys and create users on the box. But this is a very simple cloud config. So what I'm going to do now is I'm going to take a base install of CoreOS that has never been booted, give it this cloud config file, and it should bring etcd up fully configured with static IP and my SSH key so I can log into it. Right? So this is my configuration management system that's built in. So what I'll do is, there's a couple ways to use this configuration. If you're on the cloud, they usually have a metadata service that you will stick this into, and on boot up, CoreOS will pull it from the metadata service. I'm going to do this with VMware Fusion, and what I'm going to do is deliver this configuration file in a ISO image. So we have this concept of a cloud config drive. It can either be like a USB key or some small drive. In this case, I'm just going to use the ISO because it's very easy to do it in VMware. So what we're going to do is we're going to clone it on a machine. So I already have a little template that's already baked. I'm just going to do a full clone of it. I'm just going to call it etcd. Hostname really doesn't matter here. So I'm going to start it up. So the first thing I'm going to do is attach that configuration. So I just wrap that configuration in the ISO image. So I'm going to choose that ISO image, call it etcd. Now all that's in there is that YAML file that we saw earlier, in a particular layout, but just that YAML file. I'm going to connect that, and then we're going to boot the machine. So this is the provisioning process for a CoreOS image, right? You give it a config, you boot it, and that's how you're going to customize this machine. Now, if you're using a bigger environment, say you have 10,000 nodes, a lot of times you're going to do this with the Pixie process, where you're going to pass over the kernel install netboot CoreOS, and then pass over an HTTP endpoint, the cloud config you want to use for that machine. That allows you to boot a lot of machines really, really quick. And just like that, we're done. We're fully installed and configured, and now we have etcd running. So if I flip over to my terminal, I should be able to use Fleet now to list my collection of machines. Now, since the machine's already ready, so we have an IP address and there's a metadata for that machine that was configured through Cloud Management. Right? So
You're running on your Mac there. That terminal is on your Mac, not another VM.
yeah, so I'm on my Mac using VMware to handle the virtual machine. So yes, all of our tools do work on the Mac. So like this is a Fleet client that's talking to XCD to get metadata and state. So I have one machine in my cluster now, so that's XCD. I could log into it to make sure that my key works. I turn reboots off. We're up and running. Docker should be ready to go out of the box. Well, actually, we turn Docker on this machine. Oh, so on my XCD machine, and this is very important for production, I actually have mask equals true. This means Docker can't be started on this box. Why is that a good idea? You don't want to run your production workloads on the most critical component in the infrastructure. The web service you're running starts eating up all the CPU, you're going to miss heartbeats, and you're going to get timeouts, and XCD is going to fall over. And I watch people troubleshoot this, and it's really funny in the IRC watching people figure this out. Don't do that. So I mask the service. But we have one machine left. So at this point, I'm going to just start launching other machines so we can build up the rest of our cluster. And what does that look like? So we're going to do a little bit more. Remember, I want this overlay network. So in order to pull this off, here's another cloud config. Here I'm going to tell Fleet on any other machine. I don't care about these machines' IPs anymore. I'm going to tell these machines that they need to go talk to this specific XCD server that has that static IP. If we would have 5 nodes, I would have put 5 nodes in this list here, or use a DNS search right here. Here, there's some metadata. So every other machine, this machine profile I use is for a demo for Kubernetes, the high-level schedule from Google. But we can use this metadata here. And then here we're going to start, we don't want XCD on this machine, so I turn it off. We do want to start Fleet. And Flannel is that overlay network that we talked about. So what Flannel will do is it will come up. I'm going to download Flannel, which is a static binary here. And I'm going to configure Flannel to run and connect to that XCD node for its state. So we tend not to write services that use config files. Right? We usually put our configuration in the centralized store, so that way when our apps launch, they just look there. So the first thing we got to do is configure. We need to configure Flannel. So what I'll do is I'm going to write that to XCD. So I hit enter, and now we have this state in XCD. Now if I look at XCD, that's all the configuration that's in XCD right now, mainly the list that we just wrote. And if we look inside of this config, we'll see this JSON object. And that JSON object just says, here's the subnet that Flannel will have control over, and it's going to carve that up into other subnets to build this overlay network. And what it's going to do behind the scenes is it's also going to tell Docker to use the bridge set up by Flannel, so that way every container gets an IP on the network. And therefore they're all peers to each other. This is fundamentally different than the way you use Docker out of the box. And now we're just going to launch a bunch of machines. So now that we have the centralized XCD service, launching new machines, they all use the same config. IPs don't matter. They just need to know where XCD is. So we're going to spin up a couple, and then I'll take a few questions while they boot up. So what I'm going to do now is I'm just going to clone the same install. And remember, the only thing that makes these different is just is the init configuration that they get when they start up. We're just going to call this one node 0. And we're just going to do the same process so we can attach the cloud init to it. I'm just going to use the node configuration here, connect the DVD, and we'll boot that one. And while that's booting, we'll do another one. We'll just call this node 1. And what's happening as these things actually boot up, they're going to download a few things from the internet, mainly because I told them to set up Flannel. And things will happen in a certain order. Docker will be reconfigured, and these machines should come up with their new role in life. So as these boot, I'll just take a peek at Fleet really quick to see what our machines look like. So we have these machines starting to boot. The yellow one's coming up, is resolving its IP, and starting its cluster state. You had a question?
Yeah, can containers use the XCD service to synchronize?
Yes. Yeah, it's usually wide open to everyone unless you have a firewall preventing it. And ideally, when you start to share configuration between your apps, that's exactly what you want them to do, is just to go to etcd and figure out what's the database supposed to be. And this is what makes your containers portable too, right? You don't have to deal with configuration files. If every cluster you go to and you can just hit etcd, container can just start. As it moves from QA to production, it's still looking for the same key. The value will be different because you're talking to a different etcd cluster. So these machines are coming up and they'll get their IPs resolved. So the first one's up and running at this point. Now it has this new metadata. At this point, you now have the type of model where you can add any number of machines that you want to the cluster to add capacity. You don't need to know anything else other than where's etcd. You can probably use that as a DNS shortcut.
So you didn't mention where it is actually creating a bridge.
So the way Final works,
Yeah, which interface it is using.
all right, let's log in. So the way Flannel works is, Flannel will build its own interface using the ton interface adapter. And if we look at this really quick, you'll see Flannel has built its own tap, and it took one of the subnets, it carved up. So the first thing Flannel does when it boots, it says, hey, etcd, what is my configuration? And it says, well, you can carve up this subnet. And it has logic in it to do work kind of like DHCP. It can hand out subnet leases. So basically we took the 10.0.42/24 network and we bind it to this ton adapter. We've also told Docker to join a bridge and we gave Docker an IP. And the way Docker works is, by default when you have a single node in Docker, Docker's going to create a bridge with some random IP. And then any machine, any container booted on that Docker instance will just increment the IP based on what the bridge IP is. So looking at this, the next container that starts up is going to get .2. But the problem with that dynamic thing is that it doesn't work across the network. So now that Flannel's doing the bridge for you, even on Amazon or Bare Metal, you can get the same experience of having the overlay network. And this actually works over multiple hosts. You're on GCE, Amazon, and your private data center. The overlay network will do this for you. Very simple, similar to what people were doing with VPN, OpenVPN. But if you ever set up OpenVPN, it is a pain. So the next step that we're adding to Flannel is IPsec and VXLAN support. And that'll give you enough encryption to do the same thing. But the configuration will be just as simple. You'll probably put a shared key in etcd and boot up the machines and they'll all discover what they need to discover. So now we have this overlay network going. So if we were to step out of this, there's one other thing, bar run. When Flannel starts up, it writes this file out to disk, and it basically has the subnet IP that Docker needs. So it writes that down, and then when Docker boots up, we have a little place inside of our system config to tell Docker to use that environment variable, because it basically treats that as an environment variable, so it knows what IP address is set up. So the two services work together that way.
So is there a physical IP address of this that gets, sorry,
yeah, so what happens in the routing table, and we'll just look at it really quick, etcd-ctl, get, and let's spit this out really quick. So what's in there is the public IP of the guy responsible for that network, right? So that /24 can hold 254 containers. So when another container wants to talk to someone else on, say, the 42 network, what happens is Flannel will take that packet and say, well, I'm the route to get there, and I know where the next hop is, and I'll just push the packet. So you're doing this encapsulation thing. You send it to the next guy, he'll unwrap it and send it to the correct
So
container.
is that 10.0 network, is that just a LAN, a VLAN on the physical network, or is that just a completely arbitrary overlay network? That doesn't,
completely arbitrary overlay
so then
network.
you've got to, okay, and then so if that's running on a, 198, 196, whatever, local VLAN, are you doing NATs? And how do you route?
So this is just straight encapsulation. So what happens is all of these machines have an addressable IP to each other from the host level, right? They all have a...
That's totally separate.
So
It's
separate from
orthogonal
the
from
overlay.
this namespace, IP space.
Yeah, so let's log back into the machine really quick. So if you do ifconfig, the IP of the box is here, right? That got it from our DHCP server, right? That can be considered the IP for the whole network. What we do is we just build an overlay on top, and we know how to route to the next machine, not from help of any networking gear, just because we just encapsulate, and we forward that packet straight to the next hop. without any assistance from the rest of the network. So some vendors call this SDN, right? Ooh, software defined. But this is kind of the idea here, that you programmatically decouple yourself from hardware and be able to do networking like this. So
Can you show the route table?
the routing table, all right, so the route table, the way we represent the routing table, it just looks like this. So we have a collection of keys, right? So we have this key space called subnets, and that key space belongs to Flannel. Flannel then allocates subnets to each machine. So in this case, we have allocated 2 subnets. And if you look at the subnet, what do you need to do routing? You need to know where the next hop is for that particular subnet. And there it is, it's stored there. So each machine, as part of the cluster, will look at XCD and they actually do a watch. So anytime that key changes, they pick it up dynamically and update the internal routing tables. All right, so now we have this overlay network. So at this point, the containers can talk to each other, right? So now that we have this thing, we can keep adding nodes, but let's move on to something a little more exciting. So now that you have this cluster, how are you, the developer, supposed to interact with this new world, right? And we've been talking about containers all this time. So let's say we write an app, and I'm going to have a little sample app here, written in Go. It's a little hello app. All it does is say hello. Very simple, it's a web service. It binds on port 5000. And if you hit it, it should say hello. And what we do is, you have a couple of ways of doing this, but the way Docker works, and here's the workflow that most developers take, you have this Docker file. And usually you have a base image. Let's say you depended on Red Hat. This first line would say from Red Hat, or some base image that you have in some repository. What I'm using here is CoreOS has a Docker registry called quay.io. We have a hosted version of it. And on my Docker registry, I have a bunch of containers. So one of those containers is called the scratch container. So for me, in my Go binary, they don't have any third-party dependencies or dynamic libraries. So I don't need an underlying OS. All I need is just enough metadata and an empty file system. And that size of that image, right, there's about a few kilobytes for metadata. If your base image was Red Hat, it might be 50 megs to 100 megs. What we're starting to see now are people building images specifically for their apps to get that file size down, right? Because you can imagine deploying these things. But the nice thing about Docker is it has a layered file system. So if the first pull is like, let's say, a gig, the next set of pulls will only be the differences between the image on disk and the changes you've made before. So it kind of speeds up the deployments afterwards. So once we have our base image, and this can be dealt with, this can be handled by, let's say you do have an ops team. They may build a base image to have all the libraries you need for your app, or you can build them too. The next thing is just some metadata about who the maintainer is, arbitrary. And here, normally people like to build their application inside their Docker images. I don't do that, right? It makes the Docker images really, really big, and they're hard to deploy when they get that big. So what I normally do is let my build system do the compilation. And all I do is use a simple add where I take the binary in my context. So the context of Docker is wherever you are. And I just add the binary into the container. And then the next step is I say that Docker, this thing will bind on port 5000. And then here you add an entry point. So the way the containers work is they strip down what you can do. So even though there's an underlying OS in most of these containers, the init system has been replaced to only run one binary that you specified in your entry point. Now that thing can start other processes. Nothing will stop you from doing that. But the design is usually around the application, one app per container. So once you have that, you can run a series of commands to actually build a Docker image. I've already built my image, and what happens is you end up with one of these. So here's my hello container, and it has a series of layers. So the first layer is obviously my base image, which is nothing in this case, but it could have been Red Hat or Ubuntu. And each of these steps are, it's probably kind of hard to see, but each of these steps are the actual steps that it took to build a container. So like the first, this particular layer is the metadata of who the maintainer is. The next step is me adding the binary into my container. Yeah, so this particular layer is 1.2 megs, and it's the actual binary of my application. And if you're running other commands like apt-get, install, some things that your application needs, those will all be a separate layer. Why is this layering important? Because you don't want to run through those every time. Sometimes you're only updating your app source code. You don't need to install everything else. So that's our container. Once we have a container, we could log into a box and do Docker run and let Docker pull it down, but that's us having to know the host names of our machines. The whole goal of setting up a cluster like this is that we don't need to care about the host names. So what we do now is we can use Fleet. So Fleet works with systemd service files. Here's what a service file looks like. So basically, we give it a little bit of description. Here we want to make sure that this unit doesn't run until Docker is running, and mainly because we're going to be deploying a Docker container. This could have been a static binary or some other thing. And here we're basically saying we want to kill, so we're going to give this container a name, in this case hello. And if it's already running, we want to get rid of it. We're going to have a pre-start task that pulls it down, and then for the execution, we're going to delegate that to Docker and let Docker run the actual container and move on. So now what we want to do, and also I'm pinning this particular app to a machine that has the role of metadata Kubernetes. So what that means is we're going to allow Fleet to pick where this thing goes. So if we do list machines, these are all the eligible machines in the cluster, but we're going to let Fleet decide where it lands, right? So now we have this description file. We can do Fleet